the equation for statics is summation of T external is equal summation of T internal. And so what I had to do, which was incorrect, was T1 and T2 are external forces. So this should be T1 equals the things on the right, and then T2 equals the things on the right equals. So the answer here is T2, for example, is minus fx plus fy. So this is the right answer, and not the one I had. The one which I had previously had a switch in the signs. The negative was positive in my earlier. So this is the correction. Which I've incorporated here and then here. And so if you now go back to the case where I solved this problem again using Jacobians, I got an answer for the torques. So this is the answer I got from using the Jacobian method 2. This should have been negative, this should have been positive. That's what the correction I made there. And that T2 agrees with this T2, the same sign. Okay, so this is right and that is right. So my bad. So this is fixed method 1 had an error. Okay, so I'm going to update my notes on this. Okay, so let's move on from here to today's topic. We're done with using Jacobians to find velocities, angular velocities, and also the forces. Next, we'll move to dynamics, okay, beyond keeping things in static equilibrium. So this part is on dynamics, and I'll motivate this with very simple examples of a ball falling under gravity subjected to a force, and then we'll go to find the equations of motion. So equations of motion for a ball falling under gravity, that's simple, you've done that before. I'll derive the equations, do some Matlab simulations, and then go to manipulators where we'll actually use the Jacobians. So those calculations become very messy, as you see, and we'll be using a lot of symbolic toolbox in Matlab to do those computations. So I'm going to motivate this with ball falling under gravity. I'm going to make it slightly more complicated by introducing a drag force. So here is the question. Find, and this is probably a recap of things you've done in a first course in dynamics, so it shouldn't be too hard to follow this. Find equations of motion of a ball falling in gravity and subject to a quadratic drag force. Okay, how do you model the quadratic drag force? Is the force is negative c, which is a constant, times velocity squared. Okay, so c is a constant. That's how the force is, but remember we have a vector there, so vector cannot be equal to a scalar on the right. So this force acts in the direction of the velocity. So if the particle is moving in the x direction, the velocity unit vector is going to be along the x direction. If it's in the y, it's going to be in the y, and if it's moving in a general direction, v, which is along x and y, then that v is going to be a unit vector which is acting in that direction. So if the ball is moving that way, the force is going to be against the motion. Okay, where c is a constant, v is the velocity, and v hat is unit vector for the velocity. So a little bit of simplification before we go forward. So this will help us to derive the equations. When I write the drag force F, it's going to have two components in the I direction and the j direction, Fx, Fy. And I've written down the model as minus c times v square times the unit vector. So what exactly is v? I would try to write the velocity in terms of x and y, because my equations of motion will be in terms of x and y. So the formula for, well, first let me write the unit vector, which is v, the vector itself, divided by its magnitude. That is the definition of a unit vector. It's a vector divided by its magnitude. So I can effectively eliminate one of those magnitudes. So I'm left with minus c times v magnitude times vector. So let's write that down in terms of x and y. Fxi plus fyj equals minus c times x dot square plus y dot square, and the velocity is x dot I plus y dot j. So we can do is we can compare the x component, comparing both sides. We have fx, which is the force in the x direction, is minus c times x dot square plus y dot square times x dot. Right? This is the I component which I've compared. And then the fy is minus c times x dot square plus y dot square times y dot. So that's the quadratic drag model, which is actually used for most modeling purposes involving ballistics. Okay, when speed is fast and it's flowing in the air, where drag force really matters. So we'll see actually in simulations that this drag force has a huge effect when the particle is moving at high speeds. It has negligible effects when it's moving at slow speeds. So that's our drag model. So now what I'm going to do is use Newton's laws to derive an equation for a particle moving under gravity subjected to drag force. So this is, we're ready to solve this problem. Solution: always draw a free body diagram. That's the first step. Free body. I'm going to denote a free body diagram by the abbreviated by FBD. A particle under gravity. It's always a good idea to draw the coordinate axis, I and j. Okay, the drag force Fx, Fy, then we invoke the Newton's second law, which is F equals ma, right, which is mx double dot I plus my double dot j. So let's invoke that. The net force is mx double dot I plus my double dot j. So that should be equal to all the external forces acting on the body. F is the external forces. Okay, the external forces on the body are gravity. So mg is acting in the negative j direction because j upwards is positive, so negative for the direction. And then there is drag force, which is Fxi plus Fyj. Okay, so again, we have I and j on the left side, I and j on the right side. So what we do is we compare I and j components. So we have mx double dot equals plus fx. So there's only one I on the right side, so mx dot is fx. So fx we have seen is equal to minus c times x dot square plus y dot square times x dot. So this is from the drag force model I wrote down earlier. This comes from here. Let's just put 1 and 2, 1 and 2, and so this is from 1. So let me write down x double dot, which is the acceleration, which is what I'm after when I'm modeling a system, writing equations in dynamics. I'm interested in the acceleration, so that is minus c divided by m times x dot square plus y dot square times x dot. So that's my first equation. We call that pre. And then the other equation is comparing the j component from this equation. So j, j, j. So I have on the left side my double dot equals minus mg plus fy, but fy comes from 2. I derived it earlier. It's similar to this one, but x dot is on the right side is placed with y dot. So minus c minus c times x dot square plus y dot square times y dot. That comes from 2. And so I'm going to simplify this a little bit. Y double dot equals minus g minus c divided by m x dot square plus y dot square times y dot. Not anything visual, right? Free body diagrams, you have to be visual. This method is it's easy to automate this method. So Euler Lagrange method. Okay, so here is how to use the Euler Lagrange method. So we have to define something called a Lagrangian, that is k minus p. So what is L, k, and p? L is the Lagrangian. So it's the scientist called Lagrange and who came up with this method, and that's why it's called Lagrangian. K is the kinetic energy, and P is the potential energy. Okay. So write the kinetic energy, write the potential energy, find the Lagrangian, and then the equation of motion is given by this formula. Okay, it is d dt of dl dq dot, I'll tell you what dq is in a bit, dl dq equals tau k, where k goes from 1 to 3 so on. Okay, what is q? What is, this should be, what is q and what is tau? Qk is the generalized coordinate, Okay, think of this like the degree of freedom. In manipulators, we've talked about revolute joints and prismatic joints. So essentially, it is the same thing. So I would like to think of this as the degree of freedom, and then the tau k is the generalized force. So it's the generalized force associated with q. So if there is a external torque acting at joint qk, then torque 1 would be the generalized force. If there's a linear force acting there, the force would appear in that equation. If there is a viscous force, then that force would be, so the viscous force between the joints, then that force will appear there. So everything which is external force will show up there. All the internal stuff shows up in the Lagrangian as the kinetic and the potential. Everything else should be in tau k. Okay, so that's pretty much it. So that equation is all you need to derive the equations. And for 3 joints, you'll apply that equation 3 times, right? For each of this joint. That's where you'll have 3 equations, say, for a 3-link manipulator. So what I'm going to do is I'm going to show you how to use Euler Lagrange to derive the same the equations for the ball falling under gravity subject to drag force. How do you use this method? So let's redo the problem using Euler Lagrange. Redo ball falling under gravity using Euler Lagrange method. Okay, so let's first write the kinetic energy of a ball falling freely under gravity. Now the ball is, well, in addition to falling down with a speed, it's also could be moving in the x direction. So the kinetic energy is half mass times velocity squared, which is half times the velocity is x dot square plus y dot square. I can think of it's the x velocity plus the y velocity, and since I'm interested in the square, there's no square root, that goes away. And then the potential energy is minus mgy, where I'm assuming that upwards is positive. So the Lagrangian is k minus p, so that's half x dot square plus y dot square minus mgy. Okay, so now we are all set to use the Euler Lagrange formula, which is d dt dl dqk dot minus d partial dl dq k equals the generalized force. Okay, so qk, so generalized coordinates. In this case, there are 2 degrees of freedom, or the directions in which can move. The particle can move in the x direction and the y direction. So qk, one of the qk is x, the other one is y. So that way we'll have 2 equations for the 2 ways in which this thing can move, the particle can move in the x and the y direction. So let's put qk equal to y. So x is probably easier. So let's put x, and the torque or the external force in the x direction now is only the force. Is there a force? What about drag force? So drag force is in the x direction. So we have d dt dl dx dot minus dl dx equals the drag force. Okay, now this probably is the hardest for people. Let's do this. Uh, so first I do dl dx dot. For that I need to look at this formula for L. Okay, so d dt of dl dx dot. So when you're finding the derivative of L with respect to x dot, you got to treat everything except x dot to be a constant. Yeah. The k, tau k equals fx. That's the generalized force. So when you're taking this derivative for L, treat everything except x dot as a constant. So if you see the expression for L, these things are constant, only x dot is the variable. So dl dx dot would be, I'm missing a mass here. Let me just put that here. Missing a mass here and here. Okay, so half m. If I take the derivative of x dot square with respect to x dot, what should I get? 2x dot, because you treat x dot as a variable. You can think of that as a variable. So it's 2x. Yeah, I'll cancel the half, but let me just put it down. Yeah, mx. If I go further and find the derivative of y dot squared with respect to x dot, that's going to be 0 because y dot is a constant when you're taking this derivative. Similarly, y is a constant, so it's 0. So we are only left with this term for the first part. Minus dl dx. This is the derivative of L with respect to x, but there is no x showing up in the equation for L. So this term is 0 equals fx. And the final step is, well, the 2 and 2 cancels. So I take d dt of mx dot, simply mx double dot equals fx, which by the way was c times x dot square plus y dot square times x dot. And so our first equation is x double dot equals c divided by m times x dot square plus y dot square times x dot. So we got the same equation as before. We can go back and check. Here is the equation for x dot. I'm missing a, I forgot to put negative sign. Fx is actually negative, so let's put that sign, but it's the same expression. I forgot this negative sign here. This is negative, but the same expression shows up. Okay, let's do the same thing with the y degree of freedom. We'll put q k equals y. The external force, the torque, is the generalized force in the y direction is Fy, and so we have d dt of dl dy dot minus dl dy equals tau k, which is Fy, and just recollect that L is half mx dot square plus y dot square minus mgy. So let's use that over here. The first expression, the first part of that expression, dl dy dot, again we treat everything but y dot as a constant, so you'll see that you get half m times 2y dot minus dl dy. So only the last term in L has a y, minus mgy. So when I take the derivative, I would get minus mg equals fy, and then to complete this ddt, this is going to be my double dot my plus mg equals fy, which by the way was minus c times x dot square plus y dot square times y dot. And so I can write a formula for y double dot that is equal to minus g minus c divided by m x dot square plus y dot square times y dot. Okay, and we can go and check this with our previous derivation. Here it is the same expression, minus g minus c divided by m, so on and so forth. So let me write this down. We call this 4 and 5, comparing 4 and 5 with 3 and 4, we see that Euler Lagrange gives the same answer as Newton's method. Okay, so the fun part is actually when you derive it is to actually simulate this. So I'm going to show you how to actually take this, put it in Matlab, integrate these equations. Now, if this drag term was 0, c was 0, then those equations would be x double dot. So x double dot would be 0, and y double dot would be minus g. And that's something which you've learned in dynamics. You can just integrate that as an analytical solution, and you can write an analytical formula down. That's good. But if I put a drag force like this, you cannot integrate this easily. You cannot find an analytical formula. So in this case, what you should do is you want to use a numerical method to integrate equations for the acceleration. So some of the methods which you might have heard is Runge-Kutta of order 4. Euler's method is another one, a very simple method. It's something which you might have done numerical methods. I've also covered a little bit of integration when I did the differential drive kinematics. So for the differential drive kinematics, I remember I believe I used Euler's method, and then I think I showed you ODE4, which is Runge-Kutta 4, which was you've learned in numerical methods. What we'll do henceforth is we will not write our own solver, but we'll use some of the solvers in Matlab. These are ordinary differential equations, and there are methods to solve them. There is a method called ODE45 in Matlab, which I will use. It is actually a higher end version of Runge-Kutta 4. It does integration much faster than that, because in Runge-Kutta you have a fixed time step, but in ODE45 it actually is a variable time step. It's not important to know the theory for ODE45. We're just going to use this method to solve, to integrate the equation. So here is simulation, and then we'll do an animation in Matlab. I'm going to give you key things you need to do in Matlab in order to integrate the equations, and then you guys know how to animate. Once you have the trajectory, x and y as a function of time, it's just a matter of using the for loop and just going plot to get the trajectory. And then you can control the speed at which you make the plots in order to figure out, in order to get an animation which looks realistic. So I've written down the equations. Again, the same equations are derived. So these are the terminology which is used to describe these equations are ordinary differential equations. In order to describe the motion, you not only need the acceleration, you also need to specify the initial condition. Specify initial. So at time t equals 0, x0, y0, x dot 0, y dot 0 are given, where those zeros indicates the time, and the xy indicates the position of the particle, x dot y dot indicates the velocity. Okay, so implementation in Matlab. The heart of the program which I'm going to show you is this particular function. It's called ODE45, and it has, you got to give it the equations of motion. So the equations show up there. I'll show you how exactly to describe the equations. The time comes there, so you want to integrate from 0 to 5 seconds, 10 seconds will show up there. Q0 is the initial conditions, and then there are some options. How well you want it to integrate. There are tolerances on how accurate you want the integration to be. And then if you have parameters like gravity could be a parameter, and then the drag force is another parameter, you can pass it through as the last argument to this function. So let me write all those things down. This is the function that gives x dot, y dot, x double dot, y double dot. T span is time, 0 to t end. Q is the initial conditions. So this will be an array, x0, y0. Sorry, I always like to put x0, x0 dot, y0, y0 dot. These are tolerances, and these are additional parameters. Okay, example would be C, M, then G. And so those are the inputs. What it outputs is time. So so if you say 0 to 5 seconds, then it will actually give you time. If you don't specify exactly how you want discretization to take place here, then it will actually give you random points from 0 to whatever time, 0 to 5 seconds. It will also give you the state, which is basically x, y, x dot, y dot at those times. And once you have the state, x and y in particular, you can do a plot, and you can plot it. So I'm going to show you Matlab code which implements this function. And what I do is I always have something like this ready on my, I save it down and I just reuse it over and over again instead of trying to remember how the syntax of this function is. Okay, so here is this is projectile main animation. Let me see. What I have is 3 files. The main file where I would call this ODE45 and do the animation. The right hand side, this is the file which has that equation and then the animation. So let me first run the animation, play the file, main file, and show you how it looks, and then explain you a little bit about the program. This is after it does the simulation. Here's the animation. You can see that the path traced is a projectile. This happens only because I set the constant c to be 0. The drag force is 0 right here. Mass is 1, gravity is 9.81, speed was 15. So let's change the drag force and see what happens. So it doesn't have, well, it doesn't quite look like a parabola. It turns out that if you increase the speed, you'll actually see the effect of adding drag force. I'm going to increase the speed to 100. So you can see that the path is not a parabola. It's actually something like a triangle. If you increase the drag force further, you can see it becomes more of a triangle than a parabola. So this is how you actually have to shoot, let's say, a cannonball in the olden times when they had this cannonballs shooting enemies. This is the trajectory which you more likely see in a cannonball getting fired than you see a normal parabolic, because the drag force has tremendous effect on the motion of things moving really fast. Little bit about the code. My ODE45 code is right here. It has all the things I talked about, the time, the initial position. It was starting from 0, 0 at speed, which has specified options, and projectile. This is a new notation I've used, and I found it to be very effective. So what is projectile? It's basically a variable, but that variable has more variables inside it. So one way to implement or send parameters GCM is you pass 3 input parameters to that function, but that's, you have to write too much code for that. So what I do is actually pack all the G, C, and M within well, this is called actually an array. It's called a structure, where projectile.g specifies the gravity, projectile.c and projectile.m are 3 variables which are constants, and I can pass the variable projectile instead of passing c, m, and k as 3 different arguments. It's just an efficient way of doing programming, but if you like to put c, m, that's what I've done in the past, feel free to do it. TQ is the output. The function which I want to show you is the projectile RHS, which is not open. Let me open that. Okay, so here I have taken the projectile variable and unpacked G, M, and C. So this is where I would put 4 things, the equations for x dot, y dot, x double dot, y double dot. So the best way to think about functions is what is input, what is output. The output is x dot acceleration, y dot ay. Acceleration is drag force divided by m. I've written it slightly in a different way from what I wrote in the notes, just to make it super clear. That's the drag force, velocity, and so on. But essentially it is passing 4 things: the velocity, acceleration, y dot, and ay. And then the animation part, which is also target. Okay, so we launch the projectile from a particular point. We know that point. We want to hit a target. Let's call that x, d, y, d. Let's say this is given. The xy position is given. And let's say that the velocity v theta are unknown. So we do not know the velocity or the angle of launch. and we got to find that velocity and angle of launch so that we hit the target. And you of course know the physics of motion of the projectile. Now actually I've done something very similar before in the course. How do you choose v and theta to reach a particular point? This has been covered in inverse kinematics. Remember when we are tracing the figure asteroid, or with your car, with the mobile car, or with the manipulator, you are given where you want the end effector to be, and you are figuring out what the angles would be. So that is an inverse kinematics problem. This is similar to inverse kinematics in the sense you know where you want to land, and you got to choose how you launch the projectile to land there. And for that particular problem, when we were talking about mobile car or manipulator drawing figures, we use a function called fsolve. We use the same function here, fsolve, to solve the problem, except that fsolve, what it would do is it actually use integration to figure out where the projectile will land after it. So you specify v theta, it will shoot the ball and then see where it lands, and then if it doesn't land on the target, it will make corrections to v and theta so it will eventually hit the target. So this problem is similar to the inverse kinematics problem of the manipulator or differential drive car. Tracing an asteroid. Okay, so how would we use? We use the same function fsolve. So what we want to do is you want to find q0, which is our unknown. It could be in this case it's going to be v and theta. You invoke fsolve, which requires you to give the constraints, and I'll tell you what the constraints are. The initial guess, how do you want to start, with what velocity theta you start the problem with. Closer you are to the actual solution, the better it would be, but it's not required. And then options and parameters. So let me write down what these things are. This is describes the target. What's the target? It's basically x at time t minus x d y time t minus yd. In this problem, I'm also going to assume that time is given. So you want to hit the target at a specific time. Okay, this is your initial guess for v and theta. Options parameters are the same as previous, and this is going to be a solution v theta. It actually has some more parameters. Exit flag, if you remember, that exit flag tells you if the solution was found or not found. So what we'll do is essentially, this is slightly, well, let's say, you require the code which I developed previously. Previously my code, given a v and theta, it could launch the projectile for a given time, right? I have to incorporate that code within this. So what I have to do is, this is given, this xt and yt is found by integrating the equations till I hit till a time t. Okay, so for a given v and theta, I would integrate the equations. This is what I did previous to this. I'll find xt, yt. That will go within fsolve. It will find the error. Then we'll change the guess and keep change that the guess will change these two variables by integration and keep tinkering with this so that this is equal to xd and yt equals yd. So I'm going to show you code which does root solving on differential equations. Okay, so first let me run the code. What I did is a bunch of parameters. I want the target to be hit in 2 seconds, as you can see here. I launched the particle from 0, 0, and the velocity is, the position is 5 to 10 for the target. So start from 0, 0. The target is 5 on the x-axis, 10 on the y-axis. And let me first run this code and then explain you what's going on. So this is an animation of the ball hitting the target. Okay, so that v and theta was determined by the optimization. Let me confirm that. Okay, I actually changed. I did not use v and theta. I actually used the vx and vy, which is effectively specifying a v and theta. Like when you give vx and vy, effectively specifying the velocity and the angle. So this is options for the fsolve. This is the function I wrote down. Projectile constraints, QGuess options, projectile. Projectile is the parameters, mass, gravity, and so on. The constraints is the one which talks about the difference. So this is where I think the heart of the program is. This is projectile constraints. It takes in the initial guess, or sorry, the velocity, x component, the y component. It simulates. So given this function, projectile sim, takes in q0, which is the velocity in the x and y, and integrates over 2 seconds, produces q, which is the output for x and y position. Okay, so it gives an array of x and y for the different time steps. I'm only interested in the last point. So x end, q end, one is the x coordinate after 2 seconds, y is the y coordinate after 2 seconds, and I'm trying to reduce this part to 0. So x minus the target, y minus the target. So I'm trying to reduce that error to 0. That's when, once the error is 0, I've hit the target. The projectile sim is basically this function where I'm calling the ODE to integrate. It actually uses the RHS, which I've talked in the previous section. So, and then a bunch of plots. So we can change a few things. We can change 10, 10. It's the target. We can also bury the target in the ground. I believe it will work. This. We'll bury the target, the y is negative. Okay, so this is how you can shoot a basket without actually touching a ball, and you'll always get it right. Actually, there's a homework on related to this. So I'll finish here. We will talk about, we'll just continue doing